So I'm starting to.
I had a question.
Yes. Yes.
What material are we covering this week? Is it only 10.4?
No, I'm going to cover 10.5 today also. I'm going to do some exercise from 10.4, and then I will cover 10.5.
That's cool.
Okay. Okay, so hopefully Apple Pencil has charged. I may have to recharge if it is charged in the middle. Okay, now I'm going to share. There's a chat. What are the practice? Yeah, practices. So I'm going to tell you what's the practice problem for 10.4. You probably have to change a little bit. Share. Okay. So let me quickly overview cross product. Vector A, let's denote A1, A2, A3. Vector B, B1, B2, B3. Cross product as follows. A cross B. I introduced some notation yesterday, but I will follow the notation of the book this time. So cross product has 3 elements. I mean cross product, of course, it reproduces the vector, so it will contain 3 entries. First entry can be written as some number, second entry some number, third entry some number. First entry is given by the following number. Since it's the first entry, I will use only second and the third one. Second and the third one, second and the third one. I will explain the meaning of that. And the middle is the second entry. So I will question? No. So middle is second entry, therefore I use only the first and the third, skipping the second, A1, A3, B1, B3. And for here, I use -1. Last entry is the third entry, so I skip the 3 and use the first 2, A1, A2, B1, B2. And now I have to explain what's the meaning of this strange notation. The meaning is that you make a product of the diagonal direction and subtract this off diagonal direction. Same thing, product of the diagonal direction, subtract the off diagonal direction. Product of the diagonal direction, subtract the off diagonal direction. That's how you calculate. Let's quickly calculate example. For example, 1, 2, 3. Cross product.
A3, B3B, A3, B2.
Oh, yes. Yeah, I intentionally make a small mistake so that, no. Thank you so much. A2, B3, A3, B2. Great, thank you. Did I make any other mistake? Okay, thank you. So let's try to calculate, for example, this. Okay, then it's this, where the first in the first 4 numbers that we have to write is 2, 3, 0, 1, right? Here and here, and 1, 3, 1, 1 in the middle, and the last one is 1, 2, 1, 0. Got it? And therefore we have 2 times 1 minus 3 times 0, minus 1 times 1 minus 3 times 1, and 1 times 0 minus 2 times 1. So you get the vector 2 comma minus 2 comma plus 2 and minus 2. That's the answer. So you can calculate using this rather complicated algebra. Okay, now geometric meaning. The direction and the length, direction and the length of this cross product. That's the geometry meaning, right? What is the direction of this new vector and what is the length of this new vector? Okay, and direction is given by the right hand rule. So if we have vector A and vector B over here, then we put our forefinger to vector A such that the palm is towards vector B, palm direction. Vector A to the forefinger, palm towards the vector B. Then the direction of the thumb is the direction of A cross B. Therefore, this is always perpendicular to both A and B. This is direction of the thumb is directed towards the thumb using the right hand rule. Thumb. Okay, and therefore A cross B is always producing perpendicular vector to both A and B. And that's why it only works in 3 dimensions, because in 2 dimensions, if there's 2 vectors, there's no perpendicular direction, right? You can talk about the perpendicular direction to the two vector only in 3 dimensions, right? What is the length? Length is one more thing. If I have 2 vectors in the same direction, so A cross B, if both of them in same direction, then the forefinger is A and the palm cannot be B because it's the same direction. So in that case, both so if the both vector is same direction, then A cross B is 0. So you can see it from also here. So A cross B length is given by I like this fact better than the formula. So length is given by area of the parallelogram formed by the 2 vectors. And we can also write that area in terms of the formula using this theta between the 2 vectors. So theta is angle between the 2 vectors. Then this area of the parallelogram can be written as the base, right? And the height is given by B times sine theta. So that's the length that gives the length. So remember that the dot product was written in terms of the cosine theta, right? Dot product gives you a number given by the magnitude of A times magnitude of B times cosine theta. For the cross product, it's given by the sine theta. And of course, when theta is 0 means the angle between A and B is 0. And that means A and B are parallel. Or if angle is pi, which means A and B are in the opposite direction. In that case, also the vector is parallel. Even though they are opposite direction, they cannot meet no matter how long they go in that direction. So if the vector is parallel, both in the same direction or it's the opposite direction, then the corresponding angle is 0 or pi. Therefore, the cross product vanish because sine 0 and sine pi both 0. Another chat. Yeah, thumb would be coming out of the page. Yeah, that's good. So let me give an example exercise exactly motivated by that question. Okay, so now the question 14. Let me give these two vector. One is v, the other is u. And here v has longer length, as you can see, longer length, length 5. U has length 4, according to the problem. And the angle is 45 degrees. So it's some vector on the paper. Question: U cross B. So that's the vector which is perpendicular to both U and V, meaning that it should be coming out of the paper or going into the paper. Which one? That's the question. Does this vector U cross B going into the paper or coming out of the paper towards U? So for that, you have to put your 4 fingers into U, 4 fingers. And V has to be towards the palm. So
Is it going to us?
yeah, that's how I see it. So everybody get the same result. So if you place your right hand so that the 4 finger is towards you and such that the vector V is towards your palm, then the thumb is up. It's not this way. So in this case, the answer is coming out of the page towards directed into the page or out of the page. Direction directed out of the page. Okay, so I can ask such a question. What will be V cross U if you change this order between V and U instead of U cross V, but V cross U, then you can see that now the vector is going into the page. Okay, so we know the direction. To completely know what's the vector U cross B, we also need
Can you explain what you mean by like in and out of the page again?
out of the pages. So you put down the page over the desk. Out of the page means going upward, going towards you. Inwards page is going down to the ground. So yeah, just put down this this picture on your desk, U cross B, not on, yeah. So if you look at this, if you are looking at the screen, then out of the page means going to you. Into the page means going to the screen, So if you look at, if you're looking at the screen, then it's U is somewhere like that, and V is towards this direction. So you place the palm over here, and the thumb is towards you. Yeah, I should ask the camera on and see everyone's gesture doing such thing, but I hope everyone got how to get this direction. Okay, now if the direction is clear, any question about direction? So I will ask such question. I mean, it's very likely that I can ask this such question, and then I
have a question if you have time.
Sure.
So if it was a V cross U instead, it would be facing the other way, the Z direction?
Yeah, if you have a V cross U, then you have to put your 4 fingers to V, And then U is downwards, so I have to put it like that. So if I'm looking at the screen, so if the screen is vertical, V is here, U is downwards, then the thumb is that direction. It's penetrating towards the screen, right? Go behind the screen.
Okay, thank you.
You're welcome. Okay, so now no more question. Okay, now we need only the length because the direction is settled. Length, which is this one. And that's given by the product of each magnitude, which is just 5 times 4, and times sine theta. What was theta? Theta is given by 45 degrees. And therefore, the answer is 5 times 4 times 1 over square root of 2. You can simplify. Any question? Let me do the next one also. Just the direction. I'm not going to do.
Could you go back for a second?
Sure.
Okay, thank you.
Okay, so next one, V is here, U is here, and U cross V. Where does it go? U cross V, where does it go? Does it go into the screen or out of the screen towards U? Does it go away from you towards the into screen? Oh, okay, so into, everyone agrees? Everyone agrees with Yasmin? Yeah, that's the correct answer. So if you place your 4 fingers in the direction of U, and the palm must be to the direction of V, then the thumb is going into the screen. Yeah, but if my gesture is looking like going towards you, so it's confusing. But, yeah. Okay. You can always change such picture in this way. Just moving the U, just translating the U in such way, because vector doesn't matter where you put the vector. As long as you move the vector without changing the direction, then it's all same vector. So you can change U, you can move your vector such that the starting point is the same. That's up to you. Then this becomes theta. Okay, so I want to, so this will be also in the syllabus, but this is what I'm going to ask. Okay. So number 1 to 7, it asks you to prove that A cross B. So for example, number one is asking, so it gives 2 vectors, this vector and this vector. And then it asks you to prove that 6, 0, minus 2 cross 0, A, 0 is perpendicular to the above 2. Okay, now we have to prove it. What should we do? So first we have to compute this vector. So let's compute. Let's compute this vector.
I have a question. Sorry
Yes.
to interrupt, but
Yeah.
for the vectors that you just drew for U to V, aren't you supposed to, when you want to like change it into like something else, doesn't it also have to be from tail to head and then tail to head again? Like, I don't know if you know what I mean, but where you drew the other UV vector with the theta, it's tail. The 2 tails are connected, which isn't
Yeah.
like the same.
No, that's the same. So
Is
what
it?
I did is I just moved this vector u, which was here before, and I just move without changing the direction, right?
Yeah, but wouldn't the resultant be different then?
No, result cannot be different. What I'm saying is result should be
It
same.
should be the same, right?
Yeah. If you put u here and v here, still the result should be the same.
But what I don't understand. So what I'm saying is
He's
like
doing a parallelogram rule. It's the same as head to tail addition.
yeah, that's what I'm saying is like if you put the head to tail and then you put it from head to tail again, but on like the other side, like it's hard to explain without like actually showing like the drawing.
It's the same
Right.
thing. It's just called parallelogram rule. You would like do projections. It'll be the same thing though.
Okay. Yeah, I was just okay.
Okay, thanks for
you.
question and also answers. I'm sorry. I think you guys can also share your note. Okay, so yeah, there's some limitation because of this online. That part is important. So if not, then let's discuss also after the class. Okay, so let's quick computation. So here it's 0, -2, 8, 0, and here's minus sign, and 6 - 2, 0, 0, last 6, 0, 0, 8, right? And therefore, it's the vector with 16, 0, and 48. So that's the vector. We have to prove that this thing is perpendicular to both of these vectors. How to show that? Perpendicular means the vector between that and the other thing, other two vectors that we want to show that it's perpendicular, have the angle 90 degrees between, right? 90 degrees between. One property of 90 degree between means, so those facts can be proved by looking at dot products, if you remember. So because the dot products, what's the formula? The important formula of the dot product is given. The dot product of the two vector is magnitude product times cosine theta. And therefore, if theta is 90 degree, then it's vanishing. The dot product vanishing is the proof that the angle between the two vectors is 90 degrees. So we just have to show that 6, 0, -2 dot product with that one vanish. We just have to show that this is 0. That's the proof. Good. Okay, so let's calculate. That's 6 times 16 minus 2 times 48. I don't know, but it will probably 0. So you have to calculate it.
So
It's 96, right? 96. It's 96 times 96 minus 96 is 0. Therefore, A and B, not A and B. Therefore, 6, 0, -2 and 16, 0, 48 are perpendicular. That's the proof. Any question? So you can do with other vector here, I will not do it, but every time if you want to prove certain vectors perpendicular to the other, just compute the dot product and show that it becomes 0. Okay. Another.
I just have a quick question.
Yeah, sure.
So when you're using like the hand rule, can you like explain that again? I just like don't exactly understand.
Right hand rule.
Yes.
Yeah, okay. Actually, the next problem is good to explain. So let me explain using this right hand rule. So I'm going to calculate this thing. what is x-axis, y-axis, z-axis, like that, right? And this vector is I, 1, 0, 0, that's I. Question? So this is 1, 0, 0, 0, which is I. And J is over here. This is J. 0, 1, 0. Okay, now I'm going to apply the right-hand rule. Right-hand rule is using your right hand, because if you use your left hand, the answer will be opposite. Use your right hand and place your forefinger to the first vector of the cross product. In this, let's consider just the first cross product, I cross J. You put your forefingers to the first, like this, 4 fingers in the direction of the first vector I. And then the second vector J must be on the side of your palm. So palm is where your palm line is here. So palm must be over here. So this is the back of the hand. This side is the back of the hand. So the other
Your palm is up.
Oh no, here the palm is toward, so palm is like on the xj plane, but towards the y axis is the palm. Palm is facing the other vector. Yeah, palm is facing the other vector. That's better, much better expression. Yeah, I have a problem with English. The palm is toward facing the other vector here, J. So you can place your right hand such that the forefingers toward the first vector I, and the palm is facing the other vector J. Then your thumb is going upwards, right? The thumb is going to the Z direction. That's the direction of I cross J. Does it make sense?
Kinda. I just like don't understand like how you know which one to do first.
No, the first one is just whatever comes first. It's I cross J, so I is the first.
No,
If
but like on like 14 or 15, like how do you know like which one?
In 14 or 15, I will ask you the question U cross V or V cross U. So depending on what I'm asking, if I ask you U cross V, then you have to put U on your forefinger. If I ask you V cross U, then V is the first one, so you put your forefinger on the V.
And what is the purpose in doing this?
Purpose of doing it, to calculate the U cross V. So U cross V gives you the vector, right? And we want to know where is this vector directed to. This U cross V is another vector. Where is it directed to? And the way to find out is using your right hand. And you place your forefinger to the U and V, the other vector to your palm, then the direction of the thumb is the answer.
Oh, okay. So like if my like fingers are to X and then my hand is curved to Y, then like my thumb will be up.
Yeah.
Okay. Thank you.
This right hand rule is not only used here, but also when you do this electrodynamical system, if you have electric field, current inside the magnetic field. So if you have two magnets, on top and bottom, then you have magnetic field here. And you put some wire, so and you put the currents, make the currents move, then this wire starts moving. And how this wire moves is also this right hand rule. You put the magnetic field, and the wire direction to the thumb, then now the palm direction is the force, and so on. And so if you that's how the this motor is rotating. Motor is rotating because motor is some wire inside the magnetic field, so that this wire moves. That's how you make the Tesla vehicle. Right? Anyway, okay, so now we obtain the direction of this part of the vector. A cross J, I cross J is directed to Z direction, which is K direction, right? And therefore, the next step, if you want to calculate the second cross product, which is this one, then it's the K cross K. And K cross K is 0 because it's the cross product between the same vector. And we also know from this other formula that the cross product is, the length is coming with the sine theta. If they are same vector, theta will be 0, because the same vector means the angle between them is 0. And therefore, the answer here will be 0. 0 vector. Meaning the answer is not number, but it's a 0, 0, 0. Good. Okay. Yeah, so I'm skipping something from this section. One thing that I'm skipping is this question about the triple products. I'm skipping this triple products and torque. Triple products is related to how to calculate the volume of this parallelepiped, and torque is how this cross product is related to some rotating force, but I'm going to skip those two. Any question? If not, I'm going to move to the next section. Next section is equations of lines. Equations of lines in 2 dimensions is what we already graduated from, right? That's y equal ax plus b, that's standard form. We learned it very when you were very young, right? But now it's not the line in 2 dimensions, it's the equation of line in 3 dimensions. So that's why it's new. And in 3 dimensions, we also have planes. In 2 dimensions, there's only one plane. By the way, both line and plane, they are infinite object. Line infinitely long, plane infinitely spread apart, spread over. And the plane in 2 dimensions is just the whole area. Therefore, there's nothing, no special equation that describes this whole set. But in 3 dimensions, there are many planes. Plane is a subset of the whole plane, right? You can have tilted plane, horizontal plane, vertical plane. So there must be some equation that describes the plane. So all of them is in 3D. It's all about 3D. Okay. The first line. Okay. So in 2 dimension, we also learn how to write down the equation of the line given a point and the direction. Line is determined if there's a point given with a point and the direction. Right? So point can be given in 3 dimension by 3 numbers, right? So let's say a point is given by some 3 numbers. What's the good notation? Point is given by x coordinate x naught, y coordinate y naught, z coordinate z naught. This 3 number is perfect way to give a point. That's a point. Coordinate of a point. And the direction, how to give the direction? You can give a vector that points to that direction. So let's use v. Yeah, v to be the certain vector given by which number? A, B, C. A, comma, B, C. A vector pointing to the direction. Then from that, you can determine a line. What is the line? So we have R0 on the line. And we have the vector that's pointing to the direction of this line. Right? So R0 can be also viewed as, so if somewhere there must be the origin. Somewhere there must be the origin, which is 0, 0, 0. And this R0 is also representing this vector. That vector from the origin to that point is exactly the R0, right? That's the definition of the vector. Can we express any other point on the line? That's the question. Any other point on the line? Can we express this vector? And the answer is the following. Any other vector is the red plus blue, where blue is any vector that's parallel to V. Blue is any vector that's parallel to V. That's parallel to V. But can be arbitrary lengths, right? Depending on where you put these green dots on the line, this blue vector can be very, very long, or even in the opposite direction of the of the line. So V, this vector V parallel to V can be any multiple of V. You know that scalar multiplication by number t makes the vector longer or shorter or toward the opposite direction, but it doesn't change the direction, right? So that's representing the blue vector. And what is the green vector then? Green vector is exactly, if you look at this triangle, then green vector is the red vector, which is R0, plus the blue vector, which is P times V. That's the red vector. No, this is the green vector. And that should be pointing to the point that is the vector pointing to a point on the line. A point on the line. And that is for any t. That is for any t. Oh, I'm sorry. That's my spam. That's selling. That's about my social security number being hacked or something. Okay, so what is, okay, so this is point on the line, and this is for any t, which means if I collect all such if I collect all, now I want black. If I collect all this vector, so all this thing for any t can be any real number, any real number. That's the meaning that t belongs to the real number. This is the line. This is the line. It's a set of points given by those. This is representing the point. Point on the left. Okay, another way is if R is point on the line. So any point can be represented by 3 numbers, and therefore it can be also viewed as a vector, or is a vector to the point on the line. From the origin. So those 2 words are same. Point on the line. On is missing. So the vector R is either point on the line, meaning that R is 3 numbers giving me the coordinates of the point, or is equivalently it's a vector to the point on the line from the origin. This R can be written as R0 plus t times v for some t. For some t, some real number. And that's the equation. That's the equation of the line. And it has the name, since it's equation in terms of the vector, it's vector equation. I will write this as a component. So let's write R as x comma y comma z. Now, what was our notation of R naught? R naught was x naught comma y naught comma z. 1 point on the line, a given point on the line. What was our notation for the direction v? V is some number. Also, I give you a, b, c. Then this thing becomes what? So the first entry of the both sides is x on the left side, right? On the right, we have the first entry of R naught, which is x0, plus t times a. Does it make sense? That's the first entry of the left-hand side equal the first entry of the right-hand side. If you understand that part, then you can also write down the second entry of the left-hand side and the third entry of the left-hand side equal the corresponding entry of the right-hand side. Okay, these 2 equations are equivalent. It's perfectly equivalent. It's just one is using the vector notation. The other is using 3 equations for each entry. And this one it's called, the name is not important, but in the book, it's called parametric equation. I hope you remember this parametric equation at the very beginning of the semester. Here, what is the parameter? What is the parameter? So here is the parametric equation of the line. What is the parameter? P is the parameter. So if this point x naught, y naught, z naught is given, and if the direction a, b, c is given, then we can write down the parametric equation x equals some function of t, y equals some function of t, z equals some function of t. Okay, and I will give an elastic. So those two are, I said, equivalent, and this represent a line. So if you are given such expression, then you should be able to tell what kind of line it is. It's the line in which direction it passes through which point, and so on. There's another equation which is a little peculiar. Last expression is, so let me copy this parametric equation. So from this parametric equation, I will solve for t. From the first equation, what do you get? If you solve for t, then I have to move x naught to the other side, and then divide by 8, and you get t. So that's solving for t from the first equation. Good. If you understood this part, then you can find t from the second equation also, from the third equation also, right? So from the second equation, y minus y naught over b, z minus z naught over c. So they are all t, which means they are all same. So from here, you can obtain that if x, y, z are on the line, then they are all same. Any question? And this is another expression of this line. And this has a name, symmetric equation. Yeah, I don't really see the point of this name. So given in these three forms, you should recognize that it represents the same line. So let me give an example quickly. If the line has line passing through which point? 3, 4, 5, and direction directed towards 1, 2, 3, or maybe 1, 2, minus 3. Then what is the line? Those line is given by the vector r. The r is the vector pointing toward any point on the line, can be given as 3, 4, 5 plus t times 1, 2, 3 for any t, for any t real value t, plus number or minus number. So that's one representation of the line. Another representation of the line is using parametric equation, x equal 3 plus t, y equal 4 plus 2t, z equal 5 minus 3t. Can you all see what I did? I just rewrite the above vector equation in terms of three regular three equations with the parameter t. So that's the vector equation. That's parametric equation. Okay, last expression, symmetric equation. Symmetric equation is without any parameter. I think I will quickly disconnect and reconnect because now there's a lagging. Okay, let's look at the formula over here and just That's a cheat sheet. So using this formula, this is exactly x naught, y naught, z naught, a single point that given on the line, and that's the direction. So this is ABC. So we just have to use this above. So we put x minus 3 over 1. That's the first equation, equal y minus 4 over 2 equal z minus 5, 5 over minus 3. So that's the symmetric equation of the line representing the same line. So from the symmetry equation, the direction is given by the denominator. 1, 2, minus 3 is the direction, because it's ABC.
So like if you ask us like find the line like past, like if it was this question, like we just write one of the 3 equations and like that's the answer.
Yeah, if I ask, so I can also ask more specifically which equation. So write down equation with the using the parameter. Then you have to use either the first one, second, because both use the parameter p, or write down the equation of the line without parameter. Without parameter, then you have to write down the symmetry equation.
Okay, thank you.
The symmetry equation, we have 2 equal signs, right? There's 2 equal signs here and here, which means that's 2 equations. Symmetry equation is consisted of 2 equations, while the parameter equation consists of 3 equations. Yeah, it's a 1 equation in vector, but that's deceiving because vector has 3 components, so it's actually 3 equations. Okay. Okay, then I can ask the following another question. Example. So it's like the similar to this kind of question. If in 2-dimension, we all know if there's a 2-dimensional equation, you are asked a lot to find the y-intercept or x-intercept, right? X-intercept is where does it hit the x-axis. Y-intercept is where it does it hit the y-axis. If the line is given in 3 dimensions, there may not be x-intercept, right? If line can be completely avoiding the x-axis, right? X-axis is the line. 3-dimensional space is much wider space than 2-dimension. So you can draw a line that doesn't hit x-axis very easily, right? So no x-intercept in general, no y-intercept, and no z-intercept. But you can still ask, where does hit the whole xy plane? So for the above example, where the line hit the xy plane. Usually xy plane is the horizontal plane that contains the x-axis and y-axis, right? So if the line is drawn, it's very likely that it will hit xy plane. You can draw the line sort of horizontal, then it can all parallel to the xy plane, so it goes forever without hitting the xy axis. But if you draw randomly, if you draw the random line, then it will probably hit xy plane at single point. So for the above line, I can ask, where is the point that hits the xy plane? How to answer that?
Would it be where z for the symmetrical equation equals 0?
Yes,
So
exactly.
it'd be 5.
That's perfect. So xy plane, so the important fact is xy plane can be obtained by this equation. Z equals 0 is the xy plane, right? So you just plug in z equals 0. just as you described right now. Okay, so then what do you get? You get from the last symmetric equation. In the last symmetry equation, you get this equation. This equal 0 minus 5 over minus 3, which is 5 over 3. So you get two equations. One is this equal 5 over 3. Another equation, this equal 5 over 3. So you get two equations, this equal 5 over 3. And also x minus 3 over 1. This also equal 5 over 3. Everything is equal to 5 over 3. So from the first equation, of course, you will get y. Yeah, let me skip the calculation. You will get y. Okay, let's calculate it just quickly. Yeah, you get 22 over 4, 3. 22 over 3. All right? Yeah. And you can also find x by solving this equation. 14 over 3. I hope I'm right. And therefore, what is the intersecting point? The answer, intersecting point is given by the x coordinate 14 over 3, y coordinate 22 over 3, z coordinate 0. That's where the line hits the xy axis, xy plane. Good. Okay. Okay, so now let's consider with 15 minutes left. So I will consider plane in the remaining 15 minutes. Plane. So plane, some plane. I draw the boundary of the plane, but there's no boundary of the plane. Plane is infinite thing. Okay. You can pick one point in the plane, and then you can draw some vector inside the plane, right? You can draw another vector inside the plane. So plane is not determined by a single vector, right? Because you can draw two different vectors inside the plane. But still, I claim that plane can be, the direction of the plane can be obtained by single vector. So here's how. So let me repeat. So line is obtained by single direction, but the plane, you can have many vectors actually inside the plane, right? So this one vector, another vector, and all this linear combination of these two vectors, for example, this vector is also inside the plane. So every vector is infinitely many vectors inside a given plane, infinitely many directions. But still, there's one single vector that can characterize the plane. One very special vector, unique vector that can characterize the plane. That's this vector. The vector that's coming out of the plane, which is perpendicular to any other vector inside the plane. So perpendicular to two of the vector inside the plane, or of course it will be perpendicular to the whole plane. So this is normal vector. Normal is another word for perpendicular. So in mathematics, there's many words describing perpendicular characters. So normal vector, perpendicular vector, orthogonal vector that all means perpendicular, normal to the plane. And that's unique. That direction is unique, right? So we will use this normal vector to describe the plane. So normal vector is very important to describe a plane. So plane is again described by a single point. Again, I'm going to use the same notation R0. And a single vector, which is now normal vector. And normal vector, I will use the notation N because it's standing for normal. And what's the notation for the component of N? ABC was used for the component of N. Okay, so given these two numbers, a point on the plane and the normal direction to the plane, can you write down some equation that describes the plane? That's the main purpose. Okay. So let me remind you that this R0 is, again, it's a coordinate, and coordinate is also a vector at the same time. R0 is a vector from the origin to this point, right? So let me move this R0 here so that I can draw the vector. R0 is a vector from the origin to this point. Let's pick another point on the plane. Like we did on the line. Line, we want to describe arbitrary point, this green point on the line. Green point on the line. So here, let's also pick a green point on the plane. This is another point on the plane. A point on the plane. And goal is to describe this green vector. I should have used different color for the normal vector. Yeah, maybe I will just use the blue vector now. The normal vector is now blue. And this green vector is pointing to an arbitrary point on the plane. And we want to find this green vector. Okay. And to do that, we will use this vector. This dotted black vector is connecting R0, the known point, R0, to this arbitrary point on the plane. Okay, so this green vector, let's call it R, because that's what we are looking for. This R is equal to red vector plus this black vector. Let's call it, what's the black notation for black vector? And yeah, let me use P for the black vector because black vector is inside the plane. This is always inside the plane, right? Because it's connecting the 2 points in the plane. So we obtain such a vector equation. R is, of course, R0 plus this P. Because if you go to follow this red arrow, then it starts from the origin and then go to this green dots. Any question? Okay, then we get this equation. P is equal to R minus R0. I just subtracted R0 from both sides just to solve for P. Okay. And then this P is, you can see from the picture that P is part of the plane, therefore it's orthogonal or normal to this red vector, right, to the normal vector, the blue vector. Is orthogonal or perpendicular. This P is perpendicular to what? N. Got it? So let me repeat. This vector is perpendicular to N. Good. For any point on the plane, for any R, for any red, for any green R minus R naught is always perpendicular to this normal vector N. Okay, now it's the time to recall the dot product. Whenever the vector is perpendicular, what was their dot products? Dot product was given by the magnitude product times the cosine theta, and perpendicular means theta is 90 degrees. So cosine 90 is 0, so dot product vanish. So we get, so that's the answer, R minus R0 dot product with the normal vector is equal to 0. So that's the equation of the plane. So here R naught and N is given. These two are given. That's the part of the data for the plane. Then this green R is representing the point on the plane. So let me write down that in terms of X, Y, Z. So that's same thing as X comma Y comma Z, which is R, minus R naught, which is X naught, Y naught, Z naught. That's R minus R naught. Dot product with A comma B comma C. And that has to be 0. That's the equation of the plane. We can simplify the left-hand side. Left-hand side is X minus X naught, Y minus Y naught, Z minus Z naught, right? Just subtracting the two vector is subtracting each entry. And dot product, oh, Apple Pencil just died. Just 30 seconds. 30 seconds break. Any question? Anybody has any comment for 30 seconds? Okay, let me, since it's 30 seconds passed, so let's start. Pause. Okay, dot product with ABC, that's the left-hand side. And what is that? That's A times X minus X naught, B times Y minus Y naught, C times Z minus Z naught is equal to 0. That's the equation that represents the plane that pass through X naught, Y naught, Z naught and have the normal direction ABC. Okay, so compared to the line equation, we had line equation here, symmetric equation. Look at the symmetric equation because it doesn't involve the parameter. We have two equations to describe a line, but single equation to describe a plane. Why? Why is that? Single equation for describing plane, but we need two equations to describe a line. Let me give a quick answer. Because a line can be obtained in 3 dimensions by intersection of two planes. If I have one plane and another plane, then they are intersecting on a line. One plane for one equation, another plane for another equation. So two equations determines a line. Okay. That's actually good, also good question. If I have two planes, what's the line, intersecting line? Okay, so let me give, we covered some of the line, but we have to do a little more. So let me give equation, problems. 2 to 10, 21 to 32. 10.5. So we will do some of these problems tomorrow. Any question? Yeah, let's say goodbye with camera on. I'm kind of lonely. Very lonely. No, yeah, thank you. Thank you for camera on. Okay, bye, thanks. Thank you. Thank you. Thanks. Okay, then see you tomorrow.
Have a good day, Professor.
Yeah, you too. Have a good day. I have to stop recording. Right. Oh, there was a chat. Oh, yeah, thanks. Where's the stop recording? Stop.